Hello everyone, I am Akhilesh Kumar Shrivastava from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we have seen the paging schemes in the previous turns. We have also seen that how can the paging translation or the address translation be speed up with the help of the translation leukocyte buffer. Then we have seen that how can the page size, if getting bigger, be handled with the help of multi-level paging. We have discussed about the hierarchical paging, we have discussed about the inverted page table organization, and then we have seen about the hashed page table organization. In today's lecture, we will go ahead with our discussions on the paging, and we will see that how can the advantage of the paging be taken in the segmentation as well. And then finally, we will discuss about the virtual memory. So, let us start with the lecture. The scheme or the outline for the lecture would be that we will first discuss about the paging, then we will discuss about the page segmentation, and then we will have a discussion on the virtual memory. So, we have seen that the paging scheme is a scheme which divides the process into the equal size chunks known as the pages, and we divide the main memory also in the equal size chunks known as the frames, and the pages do get adjusted in the frames. Now, pages and the frames are of the equal size, and we need to maintain a page table in between that helps us in the conversion of the logical address to the physical address. So, each page table contains at least a frame number. There may be many more entries. We have seen on the last turn also that there may be a concept of the valid or the invalid bit, and there may be several other information also that can be stored in the page table. Fine. We also need to maintain a free frame list in order to allocate the pages, in order to allocate the frames to the newly coming process. Now, we have seen with this help of this diagram that what paging hardware is required for the conversion of the logical address to the physical address. The logical address issued by the CPU has two components, page number and offset. We find a frame number equivalent of the page number given with the help of the page table, and the offset remains the same as that of the logical address. The combination of the frame number and the offset is the address of the desired page in the main memory, and that address or that instruction is given to the CPU for the execution. Now, we will see today that how can the paging advantage be taken in the segmentation. Just recall the segment. What the segmentation was? It was a user view of memory or user view of process. In the user view of process, we have seen that there is a stack, array, and several other segments in the our process. Now, those segments were given the different memory, or those were given different spots in the main memory, different slots in the main memory. So, this was actually the non-contiguous allocation scheme, the segmentation. But when one process was leaving or one process was completing and the other process was coming, when we were accommodating these new segments in the holes created by the previous segments, then there are the fragmentations, and the only way by which we can deal with those fragmentation is with the compaction. So, now compaction was a very costly scheme. We also have seen this. When the compaction takes place, the CPU is busy for doing the relocation work only. It is not executing the process at that moment. So, we need to give some protection to the CPU such that it performs only the execution jobs and not the compaction like jobs. So, we have the mechanism of paging that has reduced this work. In the paging, there were literally no fragmentation. There was slight fragmentation because of the last page only, otherwise there was no fragmentation. So, we need to take the advantage of the paging in the segmentation as well. So, what we can do that each of the segments can be divided into the pages, and let us maintain a segment table for storing the information about each of the page table. Fine. I repeat that what may happen that let us say with the help of the diagram that let us maintain a segment table. There are 4 segments here. Okay, we have 4 segments. So, segment number 0, 1, 2 and 3. segment table will be containing the information about or the address about the page table of the different segments. So, for the segment number 0, this is the page table. For segment number 1, this is the page table. For segment number 2, this is the page table, and for segment number 3, this is the page table. So, the segment table is maintained to store the information about the different page tables, and the information that is required to be maintained is the address of these page table. For example, here it is mentioned that the 512 is the starting address of the first page table. So, in the main memory you can find out this page table starting at the 512 address, and the last address will be plus 63, 64 minus 1. Similarly, for this page table, for the second page table, the address will be 4096 plus the last address will be 31 plus 31. Similarly, for the next page table, the starting address is 2048, and then plus where what will be the limit of this? This will be added 2047 in this. Fine. Similarly, the page table 3 will be starting at the address 12288 and the limit is 1024. So, 1023 will be added as a last address. So, we have decided about what is the range of the addresses that will be there in the segment table, page table. So, segment table is referring to the different page tables. So, I again repeat that this is the page table of segment number 0, this is the page table of segment number 1, this is the page table for segment number 2, and this is the page table for segment number 3. Okay. So, for different segments we are maintaining the different segments, different page tables. Now, once again coming back to this page in this slide, which is telling you that what will be the logical address and how will the logical address be distributed. So, here in the logical address, let us say 32-bit address is there. In the 32-bit address, let us say the offset is of 12 bits. So, if the offset is of 12 bit, this is telling you that what is the page size. This is telling you the page size. So, 12 bits means the page size is 2 raised to the power 12 means 4 kilobyte. Now, this is the page number. This is telling you that how many maximum pages can be there in a segment. The segments may be of the different sizes, but we need to maintain a equal size, or we need to find out the maximum of the segment size. For example, let us say we have the segments of 1 kilobyte, 2 kilobyte, 4 kilobyte and 512 bytes. So, these are let us say the 4 segments. Out of these 4 segments, you can see that the largest frame segment is this one. So, to address to the largest segment we require 12 bits. So, to refer to the size of the segment we actually require this one 12 bits. So, you should remember that we are taking the largest size segment only to refer to the segment number, to refer to the offset. Now, the page number this is actually 18 bits. So, total number of pages will be 2 raised to the power 18 in one segment, and the segment number 31 and 30 means 2 bits. It means there are 2 square means 4 segments. So, this is the address split of the logical address issued by the CPU, or we divide it into the 3 parts. One part is the size of the page, then number of pages in one segment, and then the segment number, which segment number we are referring to. I again repeat that this is the 32-bit format. In the 32-bit format, the last one is referring to the page size. This is referring to number of pages in each segment, number of pages in one segment, and this is referring to the segments, number of segments. So, here we have 2 bits only. So, there will be 4 different segments. Now, this is how the address conversion is done. With the help of the paging hardware, you will be in a better position to understand this. The CPU issues a logical address. Okay, a logical address is issued by the CPU. So, this logical address contains 3 parts, as we have discussed earlier: segment number, page number and offset, or you can consider this as segment number and offset, and then finally we will divide this offset into 2 parts. So, the first is saying the segment number. So, we need to find out where my segment is or which segment we are referring to. So, we will either be referring 0, 1, 2, 3, 4 and so on and so forth in the segment number. but that is the logical numbering. So, where actually the segment is stored, we need to take help of the segment map table or segment table base register. We already have discussed about this segment table base register and segment table limit register. So, segment table base register is added in the segment number to find the entry in the segment table, and this entry in the segment table, must be telling you that what is the address of the page table for the given segment. Okay, what is the address of the page table in the given segment. So, you go in this page table and you go to the address. What you have to do? You have to find out the frame number. So, frame number will be found with respect to the page number. So, where will that page number will be in the page table? At some distance. How much distance? P distance, where P is referring to the page number. So, the page number is found from this part. So, page number, and here will be the frame number. You get the frame number from here and you get the address from here, and together with this we have the address in the main memory. I will explain it once again just to make a better understanding of the same, that we have the logical address. Logical address is containing three parts: segment number, page number and offset. So, segment number means you have the address of the segment. You have to find out the place where segment table is, and then you have to locate the given segment number there. So, segment number is given from here. You find out the appropriate entry in the segment table. In case the segment table starts from some address, let us say x. So, the value of the starting address of the segment table will be there in the segment table base register. Now, this segment table must be containing the address of the page table. So, now this will be containing the base address of the page table. So, let us say the base table is y, base address is y for this page table, this is stored here. Y, only y means y plus 0, means the address of the first page number. But if you are referring to any particular page number from here, so we will have to add that page number to find out the actual entry in this page table. So, let us say this page number is z. So, y plus z will be the entry in the page table. So, this will be containing the frame number, corresponding frame number. So, we take the frame number from here, we take the offset from here, and this entirely is telling you the physical address, means the location of your desired instruction in the main memory. So, this way we can convert the logical address to the physical address. Now, let us solve some of the problems related to this. In this problem, it is given that a page segmentation is in a page segmentation scheme, a virtual address contains 32 bits. So, let us draw this logical address split, which will have three components: segment number, page number and offset. Okay. So, 32 bit is the length of this address. What is being asked here? Out of which 12 bits are displacement. Displacement means the D. So, 12 is the displacement. 11 bits are the segment number, 9 bits are the page number. So, 11 plus 9 is 20 plus 12 32. So, what we have to calculate? We have to calculate the page size. What is the size of the page? So, obviously the offset will be telling you this. So, the page size will be 2 raised to the power 12. It means 4 kilobyte. So, 4 kilobyte is the page size. Now, what is the maximum segment size? I will go for this later, just find out some other things. Maximum number of pages. So, maximum number of pages, it may be with respect to the one segment, or it may be with respect to the entire process. So, we will also go for this later. Now, maximum number of segment, this is very easy. So, 11 is the segment number bit, and 2 raised to the power 11 will be the maximum number of segments. It means 2048 is the maximum number of segment. Why it is said maximum here? It could have been said that what is the number of segment, why we are saying that this is maximum number of segment. Let us understand it with a very small example. Let us say we have a total of 16 segments. So, the address will be of 4 digit B1, B2, B3 and B4. The 4 bit address will be there for 16 segment. Let us say the number of segment is 8. So, then we require only 3 bits B1, B2 and B3. But if we have the number of segments as 9, then also we require 4 bits. If we have the number of segments as 10, then also we require 4 bits, and in case we have 11, then also we require 4 bits. In case we have 12, 13 or 14 or 15, then also we require 4 bits only. Okay, so that is why here it is said that this number of segments can range from 1025 to 2048, but out of this the maximum is 2048. So maximum number of segments here that we have found is 2048. Now let us find out the maximum number of pages and maximum segment size. In case you refer to the only segmentation, then the address split was like segment number and offset. Together with this we were finding out the logical address. Okay. So segments or the size of the segment or the total size of the segment was referred by the D bits. So here we have segment number and the rest of the bits will be considered as the offset. Okay, let us say it is D dash. So D dash is containing actually 9 plus 12 bits, it means 21. So the segment size will be 2 raised to the power 21. Okay, so the maximum segment size here is 2 raised to the power 21. Now what will be the maximum number of pages? We are dividing each of the we are actually dividing each of the segment into the pages. So segment by segment you can say that there are 2 raised to the power 9 pages, but if you want to say how many pages are there in the total process, then it will be 2 raised to the power 11 plus 9, it means 2 raised to the power 20 pages. Refer to the logical address in the paging scheme. This was divided into the two parts, page number and the offset. Offset was the page size and this was telling you the page number. So if you consider that this address also, which is 32-bit address which is given, it is also of the kind page number and offset, then apart from the offset, rest of the bits will be in the page number. So the total number of the pages will be 11 plus 9, means 2 raised to the power 11 plus 9, that is 2 raised to the power 20. Let us solve this numerical. This is saying that in a page segmentation system, a virtual address contains 28 bits, out of which 10 bits are displacement. So this is the 28-bit logical address. There will be 3 components in this: segment number, page number and offset. 10 bits are displacement. So 10 bits are displacement with D, 9 bits are segment number and 9 bits are page number. So here it is asked that what is the page size. So obviously D will be representing the page size. So 2 raised to the power 10 means 1 kilobyte is the page size. Okay. When we are referring to 1 kilobyte, there is very much interesting thing that you should always remember, that my memory can be byte addressable or my memory can be word addressable also. Word means that we have several bytes in one go, or we can access several bytes in one go. So in that case we can say that my memory is word addressable. I can say that 1K word in that sense. Okay. So usually we do not refer to word or byte in case it is not given in the question. So in case we have D equals to 10, we will say that the size of the process is 2 raised to the power 10, it means 1K, only 1K. Okay. So word size may be 1, word size may be 2, word size may be 3, word size may be 4, usually it is in the powers of the 2. So here we are saying that 1K is the size of the page. Now maximum number of segment, that can be referred by the segment number. So 2 raised to the power 9 is the maximum number of segment, that is equals to 512. So 512 is the maximum number of segments. Similarly, maximum number of the pages. So once again you relate it with the page number and offset. Apart from the offset, rest of the part will be considered as the page number. So there will be 18 bits here. So the maximum number of pages will be 2 raised to the power 18. Okay. Similarly, maximum segment size. So once again you refer to the segmentation scheme. In that case, segment number and offset are the two parts. So apart from the segment number, that is given 9, rest of the bits will be considered as the offsets. So 19. So the maximum segment size will be 2 raised to the power 19. Okay, it means 512k. 512k. Once again, I am not referring to byte or word. So 512k, that is the maximum segment size. Let us take another example, maybe the last one for the page segmentation. In page segmentation scheme, a virtual address consists of 36 bits. So 36 bits is the logical address. So there will be three components in this: segment number, page number, and an offset. 13 bits are displacement. So 13 is here, 11 bits are segment number, and 12 bits are page number. Okay. Main memory size is 8 GB. So here we are asking some of the questions related to the main memory also. 8 GB is the main memory size. 8 GB means 2 raised to the power 33. So 33 bits will be there in the physical address. So this is the physical address. This is the logical address and this is the physical address. Calculate the following: page number. Okay. So the page number, page size. So D is referring to the page size. So 2 raised to the power 13 is the page size. Since D is 13 here, D will be 13 in the physical address also. So rest of the bit will be frame number. So 30, I am sorry, 20 bits will be there in the frame number. So last question, you can see that number of frames. So number of frames will be 2 raised to the power 20. Okay. Now physical address. So this is the physical address 20, 13, a split of 20 and 30. So this has also been answered. Now maximum number of segments. 11 are the number of bits in the segment number. So the maximum number of segments will be 2 raised to the power 11. Maximum number of pages, you relate it with the paging scheme, wherein there is page number and offset. So apart from the offset, rest of the bits will be page number. So 23 bits will be there in the page number. So maximum number of pages will be 2 raised to the power 23. Similarly, maximum segment size, you relate it with the segmentation scheme, where there are two parts: segment number and offset. Segment number is given as 11 and the offset will be a combination of last two, that is 25. So the maximum segment size will be 2 raised to the power 25. So this way we can find out. Okay, just see that here it is byte addressable. So we have to apply the bytes wherever we have found the things, like page size will be 2 raised to the power 13 bytes, maximum segment size will be this, maximum number of pages will be 2 raised to the power 23, maximum number of segment will be 2 raised to the power 11, physical address will be, okay, physical address is this one that we already have found. So we can solve several numericals like this. Now let us move to the virtual memory. Now what the virtual memory is? Virtual memory is actually the user view of the process. Okay. Now the user view of the process means process may be very big, okay, but there may not be possibility of bringing the entire process in the main memory at the same time. If the process is very big, let us say for example there is a movie and that movie has to be played, and that movie is of 2 GB, let us say, is a true SD quality 1024p kind of the movie, and it is acquiring 2 GB, let us say, space, and usually you have a 8 GB of the RAM in the current systems. So out of the 8 GB RAM, half of the part or 1/4 of the part has already been occupied by the operating system. Then you remain with either 5 GB or 6 GB, something like that. So out of the 5 GB, 6 GB, can you imagine of giving the 2 GB space only to the movie? There are several other processes also running. So it is better that you do not bring all the movie or the entire movie at the same time. You just bring a small part of that in the main memory, and when that has been played, you just send it back and bring the new part. So user view is very big, but actual space will be a smaller one, or logical space will be the smaller one. Logical address space means the logical view is big, but in physical memory we will have to bring only the fixed number of the pages or fixed number of the part only of the process. So if in case we are bringing the amount of the process only on the demand, then we will say that we are doing the demand paging. Okay. So obviously we are going ahead with the paging scheme, so we are saying that the pages will be demanded. So when the pages will be demanded, we will be bringing only the demanded pages only, not the entire all pages, not the all pages. So then what happens that the user view is big, we will have to divide the process into the pages. So where will those pages reside if not in the main memory? So we give it as space in the hard disk. Okay. So now we will say that the portion of the hard disk or the part of the hard disk is treated as the virtual memory. Okay. A part of the hard disk is treated as the virtual memory. It means that is not the RAM but being treated as the RAM. The process when created gets divided into the pages, and process when divided into the pages remains there in the hard disk, and we will bring those pages in the main memory only on demand. Okay, we will be bringing those pages only on the demand, and when the pages are not required in the main memory, we will send it back as well. Okay, you can see that some of the pages are sent out to the virtual memory and some of the pages are brought into the physical memory. So we are doing the swap out and the swap in operations, right. The user view is very big, these many pages are there in the user, from the user's point of view there are these many pages, okay. But in memory we have only limited number of pages. When we refer to any page in the main memory, then main memory map is very small for a process. We know that these are the locations of these pages in the main memory. In case that is not present, then we will bring it from the hard disk to the main memory. So this is the concept of the virtual memory. You can think of with this example also, that there is a process, there is a program, let us say A, this is completing. So we will send out the pages of this process into the hard disk space or the virtual memory space of the hard disk, and when a new process is coming in, then we will bring some of the pages of that process in the main memory. So we are bringing small parts of the program or process in the main memory. We are not bringing the entire process in the main memory in one go. So now you should also make it clear that here what we are doing, that we are using a concept of the on demand memory allocation. So whenever we are doing the on demand memory allocation, this scheme can be referred to as the demand paging. When we are dealing with the demand paging, we also require to maintain the record of what pages are there in the main memory and what pages are not there in the main memory. Hence, we have to maintain a valid and the invalid bits. For example, the logical memory is this much, that we have 8 pages, but we have accommodated only 3 pages out of that in the main memory, A, C and F. Now these pages, let's say we are referring to A, C and F, it means page number 0, 2 and 5. So page number 0 has been stored in the main memory in the frame number 4, page number 2 has also been stored in the main memory at a frame number 6, and page number 5 is also stored in the main memory in the frame number 9. But we will have to maintain the page table for all the processes. We will have to maintain the page table for all the processes, all the pages in a process. So if 8 pages are there, then we will have to maintain a page table of size 8. Out of that, only 3 entries are there in the main memory. So valid bit is enabled. But for rest of the pages, means page number 1, 3, 4, 6 and 7, we are setting up the invalid bit. So this will perhaps be making you clear more about the valid and the invalid bits, why we are taking the valid and the invalid bit. So the process may be huge, we are maintaining the page table of the size of the process, or number of entries will be equal to the number of pages in the page table, number of pages in the process. But we have only limited number of pages of that process available in the main memory. So for all those pages which are available in the main memory, the valid bit is set. For rest of the entries, invalid bit is set. So this is actually the concept of the demand paging, and this is the concept of the virtual memory, where we are allowing only the limited number of the pages in the main memory, so that we can accommodate maximum number of processes in the main memory. So we already have discussed about the valid and the invalid bit. So this is the reference for today's lecture, the Silbert, Chaz and Galvin, and on the next lecture we will discuss about the various page replacement algorithms, and we will see that how they are different from each other. Thank you for today's lecture.